Before we can talk about electric field, we must talk first about vector fields. Vector field. So, in the first semester we discussed about vectors. And but those were actually constant vectors. Any vector that we have used in katong sa ato ang in University Physics 1, mostly I think all of those are actually constant vectors. They are already specified. Okay? But vector fields are functions. Vectors which are functions. So in this case, for a three-dimensional vector field, if f is a vector field, then f is what we call a function of it can be a function of one variable or two variables or three. But in general, we can have f of x, y, z, okay, as the vector field, and it has three components. You have fx, and this fx here, unlike last time nga, ano lang siya, purely number, let's say 2i, 3j, minus 2k. Now, in the ith component, you have a function. And this could be a function of, again, x, y, z, I, plus fy, and this is another function of x, y, z, j, plus fz of x, y, z, k hat. Now, of course, this is an intermediate way of looking at vectors. Dili pa gini siya advanced, but somehow this is no longer elementary. Okay? This is a vector field. Why is it a vector field? That means that unlike a vector, a constant vector that we are used to, for example, let's say A is equal to AXI plus AYJ plus AZK. This is a constant vector. And we actually set it as pure numbers there, right? But in this case now, f and the x component is now a function. Okay? And again, it could be a function of one variable, or two variable, or of three variable. But this specifies us for every point x, y, z, it has a value. Okay? What is this x, y, z now? Now, this is any arbitrary vector. But what is x, y, z? Well, to define x, y, z here, we define the position vector as r, which is given by x I hat plus y j hat plus z k hat. This is now the position vector. So x gives us the x component of the position vector, y is the y component of the position vector, and z is the z component of the position vector. So basically, you can write this as just x, y, and z for 3 dimensions. For 2 dimensions, you can just up to dire lang, no? So x, y, and z, the same as x, y, z. That means that fx, which is the x component of f, changes as x, y, and z changes. For every point x, y, z, this will have a value. We can also name this vector f, instead of f of x, y, and z, we can also name this as f of the position vector r. F of r. But r now is a vector. So a vector which is a function of a vector. Okay, understand? Now, how does it look like? Okay, it would now, since at every point x, y, z, you will have a different value for the vector. So for example, it could be that at this point, the vector is ana. Maybe at this point, the vector is going that way. At this point, the vector is going this way. And let's say the vector is going paana dire, smaller. And here, the vector is going there. And as you can see, it's like looking at a flow of water, di ba? ano ka ng water flow, or any, like, have you seen ka ng weather forecast and then you can see the dagan sa weather, and they're represented by arrows. Now, those arrows are actually velocity vectors. Velocity vectors. And, well, of course, it changes with time. This is actually insufficient because in general, in a more, in general, f is not only a function of r, but this could also be f of x, y, z, and of time. Meaning it changes with time. So that this could be f of r of t. Okay? But this would look like upat naman ni kabuok. We already have 4. But actually, t here is a parameter. In fact, instead of writing this, we can write it this way. F of r of t, and express r in terms of t. That would be meaning parameterizing r in terms of the parameter t. But we are not going to do that one here. It's quite more advanced. It's the second level to this one. As of now, it will suffice that our vector is not time dependent. Anyway, we are in electrostatics, in which the electric field will not change in time. So, for this course, maybe we'll not be needing this one, no, as a function of time. So, you're lucky because we don't need to parameterize it in terms of time. Okay? So, nasabtan. So, just like for example, you see that the water flows like this. Of course, the vectors do not curve, right? This only means that at this point, the vector is going that way. At this point, the vector is going this way. Tangent to the curve, no? Tangent to that. Okay? So, at every point, x, y, z, this is a point x, y, z. In this case, x, y lang. It has that value. And in order to express this in terms of, to express this mathematically, we have to say that f is a function of the coordinates x, y, z. X, y, z here are called the coordinates. And this is a position vector. So, klaro dire. Okay, can you now picture out a vector field in your mind? Okay, so it's very important because here we will be dealing with vector fields, not only vectors. Okay? It's now clear what a vector. Oh, by the way, the magnitude of a vector field, magnitude of f is still written as kana. And it's still fx squared plus fy squared plus fz squared square root. But this is a function of xyz. So sa ato pa, your magnitude is a function of xyz. This is a scalar. This is the field strength. So at that specific point, evaluating this at a specific xyz, you will get the magnitude of the vector at that specific point. Right? If every specific point you have a vector, then you can get the magnitude of that vector at those points. Nasabtan ninyo? Klaro? Okay. By the way, naka-subscribe na mo? So, let's now discuss electric field. Electric field is a vector field. Okay, that's why we need to discuss the electric field. I mean the vector field first. I have to define it first before defining the electric field, because it is a vector field. And what is this field? Why is it called a field? Okay, well, it's just that you have this space and it has values in that space. Mathematically, it's not actually a field. There's what we call a definition of field in abstract algebra. This is not that belong to that, but it's just called a field because it's like seeing something that permeates space. It has an effect over a certain region. So that's why it's called a field. Okay, and yeah. So the electric charge. The electric charge is a basic fundamental property of nature. Electric charge is just like mass, it is fundamental. And it is represented by, we can actually use the Q, okay, the electric charge Q. And the unit of the electric charge is in, the unit of this is in coulombs. Coulombs. That would be, okay, in coulombs. Now, the fundamental particles of the universe has this property. Well, not all of them. Some of them have no charge. Okay, but many of these particles have charges. For example, the electron, the charge of the electron is negative 1.0602 times 10 to the negative 19 coulombs. We do not know why the electron has that charge, okay? But we know that it has that charge, okay? This is, we can represent E, the specific number E, not the E exponential in mathematics, no? In chemistry and in physics, this is usually as the charge of the electron, this constant. And it's a constant of nature. It's a fundamental constant. We do not know why it has that value. No equation will predict this value. It's just that it is. Okay? And the proton, on the other hand, the charge of the proton P is just equal to negative E. So just the positive here. So the electron and the proton, that's why your atoms are made up of electrons and protons and neutrons. How about neutrons? The charge of the neutron, let's call that Qn, is 0. Okay? The neutron is neutral. Okay? It is not affected by charges. Okay, now, so what then if we have charges? Okay? What is the big deal with charges? Well, charges give rise to what we call the electric field. Now, as long as you have a charge in space, suppose you have a particle here, and this is of charge Q, it will create an electric field emanating from this. The location of this, the electric field will be centered, or not actually centered. Yeah, actually, technically it's centered, but it depends on, maybe we have some other configurations, charge distribution also. But for as long as this is the only charge there, then the electric field emanates from here. Okay? So, how would it look like? Well, there's two charges, right? Positive or negative. If it is positive, then the arrow is going out all throughout. This is called a radially outward direction, or radially outward. This is for positive charge Q. How about for negative charge Q? For a negative charge, then it's just the same, only that the arrow is going towards this one. It's all pointing at this point here. So, but this arrow here, ako lang ni siyang gi-continue, no? But technically, at every point in space, you will have a different size of the arrow, because, di ba, we represent the magnitude of the vector as the size of the length of the arrow. So, for example, at this point here, what is the direction of the electric field? Well, all you have to do is take this radial direction, and of course, it's there. If it is positive, it's negative, it's going there. And how about at this point here? Now, for every part of this point here, kanitanan, okay, we'll have this vector field radial. Now, the thing is, what is now the magnitude of that field? Now, the electric field at a given point, for example, here, the electric field at that point, all we have to do is calculate the distance r from the source. That distance there, and the electric field here, the magnitude of the electric field there is just K Q over r squared, where K is equal to 1 over 4 pi epsilon naught. Now, epsilon naught is another fundamental constant. This is a fundamental constant of nature. This is what we call the permittivity of the vacuum. In general, if this is matter here, you get epsilon, not epsilon naught. But epsilon naught is the electric permittivity of free space, of the vacuum. No? It has a value. Okay, the value of of epsilon naught is 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. Now, that is a fundamental constant. From here, we can actually calculate K. It's easy to use just K and not include this one. Oh, well, of course, to make it more shorthand, K now will be 1 over 4 pi this. And that would give us 8.99, I think. I think this is 9.00 times 10 to the 9 Newton squared, Newton meter squared per coulomb squared. Now, for the vector form of that, okay, we are going to derive it later. But, well, if you know the magnitude of the electric field here, then what is the direction? The direction is just a radially outward, no? Or if it is negative, then it will be radially inward in this direction here. Okay? So, okay, nakuha ninyo? Now, how about if we have two or more charges in space? Then, okay, well, we can approximate that. We can actually draw that one. Suppose you have positive and you have negative here. Well, di ba, if this is not here, then the electric field padulong dito in this case, in this direction is paana, right? Like for example, in this direction, if wala ni siya, then the radial direction for this part here is ana. But since naani siya, then part of that will be taken, will be kumbaga pa kuan dire. Okay? So for example here, the electric field due to this is, let's just assume the same magnitude, no? So the electric field due to this charge here is this, right? How about the electric field due to this charge here? So since it is negative, so it's going that way, but since this is of the same charge magnitude, only opposite sign, then the arrow will be much shorter, right? Okay? Well, it could be much larger as long as the this is will increase the magnitude of this. So, what's the vector sum? The vector sum of this is kani. Parallelogram method. So, the vector sum is this. No? So, kana siya. So, instead of this vector field, nahimo na siyang ana, right? Because it is being pulled by the field here. So, technically, you will see this type of vector field, no? This type of, if you draw it like this, it would look like this. For a positive and negative charge. Okay, and why is that? For example, here, what's the field here? Well, due to this one, that would be padulong dito. Smaller, small, weaker, it's weaker. How about here? It's near, so stronger, so the vector sum will be this. So, at this point here, the vector field is going like that, right? And if you trace this, you can see that it's going this way, ang yahang curved lines. Okay? So this is now the vector field for positive and negative. Okay, now how about both pag like signs? Pag like signs, then instead of like signs repel, opposite signs attract. So in this case, we have positive and positive. So, paano, no? It will, for example, dire, nganong mutulak siya dire because this will create a murag tulakon siya dire, no? On this side. So, mura siya paana karon, no? Okay. How about pag negative? If negative, then it will be the same curves nga makita nimo, but the arrow is going towards the charges. Nasabtan? Okay. So, now that you have na-imagine na ninyo unsa ang setup dire. So we are now ready to formalize this into the language of vector fields. The functions called vector fields. Okay? So, if this is the charge here, and if we take the charges at the origin, and this is the position, the point P. So in order to calculate the electric field, we need a charge. Now, if there's no charge, there's no electric field. The charge is the source of the electric field. So we need the field and we need the point P. It's called the point of evaluation. Okay? The point of evaluation. And we need the vector from the charge pointing towards the point of evaluation. And let's call this vector R. Okay? Now, depending on the magnitude of the field, okay, the direction of this R is always going from the charge. R is going from the charge towards the point of evaluation. Okay? So, maunay, kuan. It's going from the charge towards the point of evaluation. That's the direction of R. Take note of that. Okay? Because when we get into many combination of charges, you should take note of this position vector or this one. Let's call that R. And this R here is, of course, you can calculate this, right? So what's the electric field? So di ba ang electric field would just be either going this way or going that way, depending on the sign of the charge. And in fact, we can calculate now the electric field at point P. So this is the electric field at point P, or we can call this the E of R. E at R is KQ over R. Di ba ganiha from our formula, it's the distance, the square of the distance. So what's the distance? That's just the magnitude R, right? That's just the magnitude R. Pero kinahanglan man gud nato ni siya butangan pod og this is a vector. This is square. This is a vector here, and this one is not yet a vector. We have to make this into a vector, but of course, luckily, we know the direction of this. We know that the direction of the electric field is either parallel to R or anti-parallel to R. If it is negative, it's pointing towards there. No, it's either pointing towards here, which is parallel to R, or anti-parallel. Parallel, actually, as long as it's collinear. No? Anti-parallel that's collinear, pero on the opposite direction. So, yeah, it's either that. It would now depend on the sign of the charge, if it's positive or negative. Now, to give this one, all we have to do is find a unit vector that is parallel to R. Now, how do we find a unit vector parallel to R? Well, we have done that in our previous course, and that we call that R hat, the unit vector parallel to R. And this is just equal to R over the magnitude of R. So that means to convert this into the vector, we need to multiply this by the vector R and its magnitude, over its magnitude. So now we can now calculate, we have now this final form, the electric field at R equals KQ over the magnitude of R cubed times R, the vector R. Okay? Or in some books, instead of seeing this, you can see it's KQ over R squared times R hat. Notice the difference. Squared and then this is R hat. Right? So, I'd like to use this one instead of this one. Because this one, you need to calculate R hat first. Okay? Now, notice that this is a whole scalar, right? Ato ni siyang i-analyze based sa atong knowledge sa katuganing vector multiplication. Let's analyze this one. This whole thing is a scalar, and this is the vector. So this is just a whole scalar times the vector. And we know that the scalar times the vector doesn't change the direction. It's either it moves ana or it could change direction, but on the still collinear. It doesn't change the vector in a different kumbaga pa outside the line that joins them. Okay? So if it is positive, ana siya, I mean, depende. If this is the positive direction, so a positive would that be, if that's the original direction, and if you multiply it by a negative, it will reverse, right? So meaning the direction of E is just either parallel to R or anti-parallel to R. It would be anti-parallel if this is negative, tama? Ako ninyo? It would be anti-parallel if it is negative, kaya maano man siya. Okay? Or it will be, pag positive, well, of course, ana lang siya. So, have you now, nasabtan na ni siya? Okay? You understand this now? Okay? For me, I would love to use this one. Okay? In some books, actually, okay, anyway, kuha na nato na siya. Okay, erase na ako na siya. Now, in this case, okay, this is the charge Q, ha. In this case, we put the charge Q at the origin. But it's just okay if we have a single charge. But what about if we have multiple charges in space? So, there's no reason now that we must put the charge at the origin. In fact, the origin could be arbitrary. So, we have to revise this formula in order to put the in order to have this, to derive a formula for the electric field whenever that the charge is not at the origin. Okay? So put this as the origin, and you have now a charge there, which has, this is the position vector of that, and we call this now our R. Nakuha. And, di ba, we need a charge and a point of evaluation. So suppose that this is our point of evaluation. This is, let's call that point P, the point of evaluation. So, we also need to know the location of this point, right? Okay? We need to know the location of the point P because point P is given in terms of the origin of this coordinate system. But, di ba, also may kinahanglan nato. Okay, let's call this, this is R, let's call this RP na lang. Okay? We'll call that RP. The location of point P. Okay? Now, also may need nato, di ba, we need that vector coming from the charge padulong sa point of evaluation. That means that this is not what we actually need. What we need is this vector here. And that is now, katong ganiha, that would now be R. But the point is, ato namang gibutang ang R diri, let's just name this as our R prime. Okay? And let's express R prime in terms of R and RP because in general, in actual problem, in the real world, we would know R and RP. Okay? So let's find this R here in terms of that. Well, of course, this is a simple vector addition. This plus that equals that, diba? So vector addition. So sa ato pa, R plus R prime equals RP. Now, you have to take note of our notation because if you read some books or if you watch some other videos, okay? Of course, my videos will be sufficient. But if you need to watch other videos, you have to take note of the notation. Okay? So, pero paningkamutan ako nga, ang atong videos lang daan is sapat na. Ako lang sapat na. Wala akong paningkamutan, no? Okay, para di na mamutan na uglain. Okay? So, sa ato pa here, R prime equals RP minus R. Right? So we now have this R prime. This is what we need, right? So if we plug in this, so the formula, what was the formula? I erased it, but what was the formula? E of, the E at P now, I'll just put it at P. Okay? Or E at RP na lang. E at RP is equal to, okay, I'm not comfortable putting RP here. E is equal to, E at point P na lang no? E at point P. This is KQ over this vector, right? So, that would be the magnitude of R minus R prime. Sorry. R minus RP. Sorry. Okay. RP minus R cube times R minus, okay, RP minus R. Okay? So this is just, that's the formula now. Okay, all of this plug in. So for example, let's say Q equals 2 columns and located at, let's just use 2 dimension lang R to be, the location of this is at, let's say 1, 4, and our R, our point of evaluation, point P is given by, point P is, let's say, kanina lang, no? This is 4, 5, this may be 7, 5. Or actually, we can say that this is, our R is 7I hat plus 5J hat. Okay? So, what would be the electric field at that point? Well, first find RP minus R. This is our, in this case, this is our R. And this one is RP. So, this vector here, RP minus R, would give us RP minus R, as atong R. So 7 minus 1, that would be 6. 5 minus 4, that would be 1. Okay? Or you can write this in terms of, okay, by the way, this is in meters, we have to use meters here, standard units. Okay? Because we're using column. So, okay? So, if it is not given in meters, you have to convert it into meters. So, we have this, or we can say that this is 6I plus J. Now, what's the magnitude? RP minus R is, well, it's just 36 plus 1, right? So, this is 6 squared plus 1 squared, square root, and that would give you square root of 37. This is in meters. Okay? Okay. Okay, we now have this and we now have that. Okay, so we can now find the electric field at, asa man nato ni butang? Okay, we can now find the electric field at point this, right? And let's just label that as 7. The electric field at 7.5 is KQ, so this is 9 times 10 to the 9 Newton meter squared per column squared times our charge, 2 columns. So 2 columns over square root of 37 meter, this is cube, times 6 meter, 1 meter, no? This vector. Now, of course, let's look at now the units. This will cancel out. This is meter squared and this is meter. So, this will be meter cube sa taas. In the numerator, we have meter cube. And sa ubos, natay meter cube. So, sa ato pa, meters will cancel out. Also, you have column and I-column diri. So, what is left is over Newton per column. The unit of electric field is newtons per column. Okay? Now, you will understand later why is that, what's the meaning, why newtons per coulomb. Okay, because that is a force per unit charge. In fact, that's what the electric field is. The force per unit charge. Anyway, so, okay, kindly do this in your calculator. Kani siya, ang first lang sa ta. This 9 times 10 to the 9. Okay, to avoid very large number, let's just use 2 nanocoulomb dire. 2 nanocoulomb. So sa ato pa, this would now become times 2 times 10 to the negative 9 coulombs, no? Let's just use 2 nanocoulombs to avoid very large numbers. Because 1 coulomb is actually, so 1 nanocoulomb is times 10 to the negative 9 coulombs. So pila ni siya? 9. So mag-cancel ni actually ning 10 to the 9 and 10 to the 9, right? So you have 9 times 2, that's 18. Over square root of 37. Can you do this in your calculator, be? Kanilang sang dire. No? Ha? Wala. Ayos na sa 6. Kay atong audience manggod para dili mabigla atong audience. Mga gatanaw. Tanaw diri po, di ba? Okay? Wala? So, this whole thing is 0.0 isa lang? 0.07 99 998. So, 0.998. 998 na lang. Sige, data. Times 6.1. Of course, the whole unit now will be newtons per coulomb, no? So, this is times 6 pila. Ha? Pila? 0.479989. O, for 0.48 na lang. No? 0.48 newtons per coulomb. This is on the I. So, right? This is on the I. And this is also, will give us positive. So, this is now plus 0.08 newtons per coulomb J hat. This is now our electric field vector at the point 0.75. Sabtan. Okay. Now, suppose we want to calculate we also want the magnitude. What's the magnitude? The magnitude of this one, the magnitude of E now is pila. Of course, you take the square of this, so 0.48 squared plus 0.08 squared, square root equals pila? 0.486. 486 newtons per coulomb. That's the magnitude of the electric field at that point. Lak. Hindi na makita. Diri ba kay na ay ano dito? Asa na ta? 487. 487? Okay. So, 487. Or let's just use 49. Okay? 0.49 Newton per coulomb squared. Okay, so you know now, nasabtan ni siya, at least for one charge. Now, what if we have multiple charges? Well, it's no problem. Because we know that the property, we know how to add vectors, right? So all we have to do is add vectors at that point. So suppose that we have, let's say we have, let's say Q1 here, and let's say Q2, and let's say Q3. And let's evaluate this. This is our point of evaluation. So all we have to do is identify the vectors at the locations of Q1, Q2, Q3. No, let's call this R1, R2, and R3. And of course, this is still our RP. So what we need is this. This is, let's call this R1 prime. And we also need this vector from Q2 to RP, right? So let's call this R2 prime. And from R3 to point P, right? Let's call this R3 prime. So, of course, we can just easily, we know the formula of this. What is R1 prime? R1 prime is just RP minus R1, right? And R2 prime would be RP minus R2. And R3 prime would be RP minus R3. Now, R1 is the location of charge 1, R2 is the location of charge 2, and R3 is the location of charge 3. Okay. What is then on, and so on. You can have Q4, Q5, and so on. No? So all we need is this. The total electric field at point P will be, of course, the electric field at point P due to Q1. Okay, let's call this point, this is E1 plus E2 plus, of course, pila na sila. Okay, that's just formula. But what is the electric field at point P due to E1? Let's call this 1P, 2P, and so on. No? We can plug in the formula directly. This is just, this one is K, Q1, of course, over that RP minus R1 cube times RP minus R1 plus KQ2 over RP minus R2 times, this is cube times RP minus R2 plus and so on. Okay? So all you have to do is add. If you know how to calculate one, you can now calculate all. All you have to do at the end is add all those vectors by vector addition. No? Now, okay, how about we have point charges. We know how to calculate the electric field for point charges. But in reality, we will not be dealing with point charges. We will be dealing with distribution of charges, continuous distribution of charge. For example, instead of a point, we might be interested with calculating the electric field of a line. And of course, the line it's not a point to begin with. Okay? And the line is actually made up of how many points making a line? How many points making a line? 2? No, 2 points is needed to construct a line. I mean, to connecting the 2 points, right? But in order to make a line, you need infinite number of points. So that means, okay, sa ato pa, the line is made up of infinite number of point charges there. Actually, in reality, it's not really infinite, but so many. Avogadro's number level. Okay? So, still, that's infinite. So, let's assume that that's an infinite number of lines here, of charges here. So, whenever we want to calculate the electric field at a specific point here, then, ibig sabihin, we must calculate the electric field for each point and do the summation. So, from this one, you will know that this will involve integration. Because whenever there's integration is nothing but infinite summation. But not only infinite summation, it's actually taking the changes of that as you approach to 0. Ibig sabihin, you are summing infinitely many times, but at the same time, the interval in which you are summing is so small that it is called infinitesimally small. So in that case, we can still use our formula, but we have to, okay, modify it. Okay? So, let's begin. Let's calculate the electric field of a finite line lang of a line of length L. This is a line of charge of length L. Now, to deal with this one, instead of charges, we will be talking about charge densities. First, we must talk about charge density. We have three types of charge density. Lambda, which is the linear charge density. And the unit of lambda is in Newton per, coulomb per meter. And you have sigma whenever we're dealing with the surface. That would be surface charge density. And this would be coulomb meter squared. And we have rho, which is the volume charge density. And this would be coulomb per meter cube. Okay? So in this case, okay, by the way, what is charge density? That is the total charge over the total, if we are in linear, so the total charge over the length. So that means that we can take this as the total charge, some total charge Q over the length L. This one is the total charge Q over the area, and this one here is the total charge Q over the volume. But there are cases in which we do not know we may not be able to know the total charge, or we don't need to know the total charge. All we need is the charge density. So in this case, of course, this is finite. Since this is finite, we can get some total charge here. So let's assume that this is a total charge Q. So let's calculate the electric field due to this charge distribution here. So, well, of course, asa natin i-calculate? Okay? Now, I will calculate it in a specific point, but I'm going to give you as a problem, as something to pass on Monday, no, on Tuesday. Okay? Evaluate at any point P. Okay? Now, I will just evaluate this as a specific point here. My P is, this is symmetric. Okay? I will evaluate this as a symmetric. This is at a point of symmetry here. Now, let's give this P the point some A, 0. We are in two dimensions. So this point here is A, 0. Okay? So we want to calculate the electric field now. This is symmetric. And this is right at the center. So sa ato pa, what's the coordinates? That would be 0, L. And this one would be 0, negative L. Now, humano na lang nato ni ha, kay, para mahatag na ako sa inyong problem. Okay? Anyway, wala man tayo klase karong kuan. So what we need now is, okay, to start with, we do not yet know how to calculate the electric field of a line. But what we know so far is calculate the electric field of a point. So, in order to do that, we have to convert this line into a series of points. Series of point interval points. It's not actually points, but it's a discrete point. Assuming that this is a point, and let the point to have the length. Let this to have a differential length of dy. It is so small that it is, okay, let's call that dy, infinitesimally small. Okay? Now the question is, what is now the charge of that small dy? Well, we can use the charge density, the linear charge density, to calculate for that very small, right? If for the whole length you have q, then how about that? Well, it's simple. Lambda, since lambda is constant, lambda is equal to, given ang q diri na, let's give this as total charge q and length L, q over L, and this must also be dq, the charge of this lambda, the charge of this, small charge, that's dq, over the length, which is dy. So from here, we can see that dq equals what? Q over L dy. Or we can just let this as lambda, although lambda is not given, but we can just calculate lambda from Q and L. No? Lambda dy. Okay, so we now have what's the location of this now? Well, the vector location of that, our R, the vector R, this is our RP, right? Tama? This one here is our RP, which is given by A0. Sa ato pa, this vector R here is given by 0 and the coordinates would be Y. Y is arbitrary, any point on that. So what is now the electric field due to that? Well, that's just the electric field that this, paani, well, this is, we know that this is just Rp minus R, right? Let's calculate that. Rp minus R would be what? A minus 0, that would be A. 0 minus L. Sorry, this is L, this must be L over 2. Okay? L over 2. No? So, okay, that is 0 minus Y. That is negative Y. So this is now L over 2, and this is minus L over 2. Okay? So we now have this. So the magnitude of that, Rp minus R, is just equal to A squared plus Y squared square root. And this is, okay, muna siya. So what is now our electric field? Our electric field would be, the electric field due to this charge there, since this is charge dq, okay, so let's call that dE. dE now, at P, would be equal to K dq over that. So A squared plus Y squared raised to 3 halves, right? And this is A negative Y. This will have 2 integrals here. Okay, by the way, so our E actually is the integral of K. Let's replace dq by lambda dy. So K lambda dy, because ang atong variable dire is not q but y. Right? So lambda dy over A squared plus Y squared. Okay, times AY. So I'll just lambda A dy I hat plus the integral of, okay, may mo ni siyang minus, K lambda Y dy over A squared plus Y squared raised, okay, sorry, this is 3 halves, no? 3 halves. So this is 3 halves. Okay? Now, I will argue, but you have to, okay, you have, this is very easy. I'm going to say that, okay, by the way, what's the limit of integration? That would be from negative L over 2 to L over 2. Negative L over 2 to L over 2. Our Y runs from this to that. Kana siya. And I will claim that this is 0, but you have to prove that this is 0 by integrating this one. No, kaya na ninyo na. So I will integrate this one here. Okay? So, why is this 0? Because of symmetry. I can set that to 0. So this is symmetric. This one will give a field going into that, assuming positive. But on the other side, because this is symmetric, kung unsay naa diri iyahang bawion diri, right? This will also give a charge nga paana dito, a field paana. So you see that the y's will cancel out, right? And what would remain is the x. So by looking into the geometry and by arguing to symmetry, I can say that this is 0. Now, this is all is left to be integrated. So how do we integrate this one now? Okay, we have, let's call this EX. So we know now that EY equals 0. So clearly our final electric field would be on one direction. Okay? So, EX now would be K lambda A, the integral of minus L over 2 to L over 2 of dy over A squared plus Y squared raised to 3 halves. Now, we integrate this by trigonometric substitution by letting y equals A tangent x. So that dy now becomes A secant squared x dx. So this will be, dy will be replaced by this. So what would happen to the equation? We have now K lambda A, the integral, let's not put the limit now because it has changed. You have A secant squared x dx over. Now what happens to this? You have A tangent squared, right? A tangent squared, A squared tangent squared. We can check out A and A squared. A squared raised to 3 halves becomes A cube, right? So now A cube diri. Okay. Now we have 1 plus tangent squared. Shortcut na ako, but you have to do the calculations on your own. I will leave every derivation, I will leave something for you to derive. Kaya kung ihatag na ako na, yun na lang ang memorization. No, ibig sabihin, akong skip dire. Okay? So, this will be 1 plus tangent squared, which is secant squared. Secant squared raised to 3 halves is secant cube. So, this is now times secant cube x dx. What is left? Okay. Cancel. May A dira. What is left now would be, okay, cancel ang cube, right? So you will have now the integral of cosine, right? Tama? Okay, ganun lang, equals 3. Okay? You will have the integral of cosine. What's the integral of cosine? So this whole thing becomes the integral of cos x dx. So this is now equal to k lambda over a. The integral of cosine is sine x times sine x. But, okay, how do we have to go to balik ta dire. This is our assumption. So, sa ato pa, this will be our, if this is our x, then this is our y. So, this is square root of a squared plus y squared, right? From this. Tanawa. Tangent x is y over a. Sa ato pa morning a, right? Because tangent is opposite over adjacent. So this must be a squared plus y squared. So what is now sine? Sine is opposite, which is y over hypotenuse. So this means that this is just equal to, okay, ako nang idiretso ha, this is now equal to k times y over square root of a squared plus y squared, evaluated from minus L over 2 to L over 2. So, ano na ninyo dire? Minus, di ba? This minus that limit. And you can see that the electric field, ako na siyang ikuan dire, would be Ka, L over 2. You have minus negative L over 2, so you have L over 2 plus L over 2, right? That would be L. Tama? L over 2 minus negative L over 2. That would be L. Kaning diri pareho. So here, you would now have K lambda over A times this becomes L over, this is L over A squared plus L squared. So this is L over A squared plus L squared over 4 square root. This is now my EX. So sa ato pa, my electric field here, the electric field would be, at point P would be K lambda L over A square root of A squared plus L squared over 4 I hat. For your problem set number 1, calculate the electric field at any point P. I calculated it with symmetry. Now, I want you to calculate the electric field at any point. At any point. So, meaning, point P now will be given by X, Y. Okay? This is a constant. Do not use that Y. We can call it X naught, Y naught. For any X naught, Y naught, calculate the electric. This is a constant, no? For any location in space, calculate the electric field and show that if you let X naught, Y naught as A and 0, you will get our result. You can check that. Masabtan? Calculate the electric field at any point X naught, Y naught. So wala na symmetry diri. Meaning the integral along Y will also no longer be 0. Okay, that is to be passed on. Ano, isa naman na. I-pass ninyo before mumuha. Kano sa mumuhawa? Kadlawon sa Friday o Thursday? Isa na kabuok. Namoy long exam ka no sa? Wednesday? Thursday yung sa oras. Ha? O, di 7. Ako boy, whole day nga mo. Ako na lang pirmi nagaparaya, guys. Pati ba naman sa klase, ako'y magparaya? Muna lang na akong role sa akong kinabuhi ang magparaya. Pagod na ako. Okay, sige, Monday. Tuesday. Okay? Sa sunod, din ako magparaya. Dapat lumigaya naman ako. Okay?